Welcome to Astronomy at the Beach. This presentation is Size and Distance in the Universe, given by Ken Bertin. And Ken is quite a presenter. He's been a hobbyist astronomer for 68 years. Importantly, he's a NASA Solar System Ambassador. And he's a lifetime member of the Warren Astronomical Society, where he's been a president and also a vice president over the years. And amazingly, Ken was just telling me he has traveled the globe to see 10 total solar eclipses. 10. 4 annuals, 7 transits of Mercury, a couple transits of Venus, and 15 lunar eclipses. Wow, he's quite the astronomy traveler. He's given over 500 presentations to astronomy clubs, schools, and social organizations. And I've heard him speak, and one of the things that I would encourage folks is he's a great guy to talk to if you're young, you love astronomy, and you're thinking of making it your profession. Talk to Ken. He's got some good counsel. So I'd like to throw it to Ken to give tonight's presentation. And before I leave, I would like to say, go ahead and chat questions into your YouTube chat. I'll be monitoring them. And at the end, Ken will ask for questions, and I'll throw him some of the good ones, and we'll get to as many as we can. Thanks.
Thanks very much, Brian. One of the things that comes up with many people in astronomy is trying to figure out this vast universe of ours. It is really, really much larger than the mind can grasp, and we don't even know if we've seen the limit of it. But what tonight I'm going to do is I'm going to kind of bring it down to the novice's idea, as to get a kind of an idea of things that with which you're familiar, and tell you how you can tell distances and sizes in the universe. And so this is called Size and Distance in the Universe. And of all my presentations, this is one of my very favorites. So after we're done here, we'll go and talk about it. First of all, let's say one thing right now: the universe is very large. So what we're going to do now is we want to take our car, and every one of you have probably been in a car going 60 miles per hour. And if you decided to drive to California, you would get there in approximately 24 hours of continuous driving. Now, let's say that you wanted to drive to California, for example. Well, if we decided to drive to California and you continued to drive, it would take you about 3 days to get to California. Okay, so we all know that. That's pretty easy. Many of you probably have taken that drive, I'm sure, to Florida, perhaps to California as well. What we're going to do now is we're going to take our car and we're going to put a road all the way around the Earth. And what we're going to do is we're going to drive that car around the Earth. And how long is it going to take us? It's going to take us 17 days. So if you drove continuously without stopping around the Earth, it would take you 17 days. By the way, if you drove around the moon, for example, it would take you 5 days to get around the moon. And if you decided to drive around the sun, it would take you 2 years, just to give you an idea of how huge the sun is and how small the moon is. Let's drive to the moon. To the moon. Well, to the moon, it took the astronauts 3 days in the Apollo capsule, but in our car, it's going to take us, let's see, how about 160 days, about 5 months. Is about the right time, and that would be in your car going 60 miles per hour. Well, let's go drive to the sun. Now on the sun, guess how long it takes? Farther than the moon, of course, but how much farther? The moon and the sun appear to be similar in size, but the sun is much larger. It would take our car to drive to the sun at 60 miles per hour 177 years. Well, the sun is 4 times larger. The sun is 400 times larger than the moon, and it is also 400 times farther away. So when you have an eclipse, you get If you get an eclipse, you see that the moon and the sun are about the same size. Now we're going to drive to the farthest planet in the solar system. We're going to drive to Neptune. And driving to Neptune is, of course, farther than the sun. And it is going to take us to get to Neptune 5,133 years. 5,133 years. So you better get your car souped up to do that. Now what we're going to do is we're going to drive our car to Proxima Centauri. That's the closest star to the solar system. And we better gas up the car pretty good, because going to that Proxima Centauri, it is a southern hemisphere star, so we don't get to see it from here. It is in the Alpha Centauri main star in Rigel Kentaurus system. Thus, how long would it take us? At 60 miles per hour, it will take us 47 million years to drive at 60 miles per hour to the very closest star, of course, aside from the sun. Let's take a little trip in our car across the galaxy. This is our Milky Way galaxy. This Milky Way galaxy is made up of some 200 billion stars, maybe a little more, maybe a little less. And we're going to travel across it, and it's going to take us 1,106,000,000 years, 1,106,000,000 years to get across the Milky Way. How about driving to the closest galaxy like our own? That spiral galaxy called Andromeda Galaxy. Andromeda, or M31, one we can see with our unaided eye, although it's rather dim. If you wanted to drive there and you drove at 60 miles per hour, it would take you 23 trillion years to get there. 23 trillion years. That is one of the closest galaxies among the 500 billion to a trillion galaxies that we know of. Count to a billion at 1 a second, it would take you 31 years to count that high. Now, obviously, you can't drive a car to the stars. So what we're going to do is we're going to speed it up a bit, and we're going to go the fastest speed that you can go by physics, and that's the speed of light, which is 186,283 miles per second. Okay? Now, again, it could be 284, it could be 282, I'm not sure for sure, but it's 186,280 miles per second. So let's take this rocket ship and we soup it up. We'll travel as fast as we can do, and we'll go to Florida. And how long is it going to take us to Florida? Well, we're going to get to go back and forth from Florida 120 times each second. And as far as California is concerned, 40 times a second. Well, I'm going to throw something else at you right now. Let's go around the Earth, taking our rocket ship at 186,000 miles per second. By the way, the ISS takes 90 minutes to get around. We're going to take that rocket ship and fly it around. And how long do you suppose it's going to take? Well, we're going to get to go around it 7 times each second. So if you take a globe of the Earth and you took your finger around it, you couldn't do it 7 times in 1 second, to give you an idea. Now what we're going to do is we're going to go to the moon, but we're going to do something special this time. We're going to give telephones out. Now, telephones, the speed that the radio signal goes from telephone to telephone is the speed of light. So what we're going to do is we're now going to talk on the phone instead. And what we're going to do, it's going to turn out better than a rocket ship. So let's take 2 of you, and what we're going to do, we're going to send one of the people to the moon and give them each a phone. And one of the people is going to say hello to the other person. So let's say we have John and Mary here, and John is here, and John says, hello, Mary. And it's going to take 1.2 seconds to get that information there. So there's a little bit of a delay. Like, for example, when we have people on the moon, they are delayed just slightly in their conversation. Okay, now we're going to go to the sun, and we're going to leave send Mary to the sun. We're going to leave John here on the Earth, and John is going to say hello to Mary. Hello, Mary, and Mary is going to hear from him in 8 minutes. So 8 minutes from now, that would be 8:48, I guess, and that's when they'll first hear from each other. So the conversation would go hello. 8 minutes later, hello. Another 8 minutes, say hello. So the conversation will take a while. That's to the sun. Now we're going to talk about Neptune. Hello, John says to Mary. Well, it's 8:40 right now. 5 hours from now, she's going to hear from him. Now, understand that this also poses a problem. So if we have a spaceship up there and something goes wrong, and we're at Neptune with the spaceship, and something goes wrong, we don't find out about it for 5 hours. And then not only do we not find out for 5 hours, if you're going to fix it, you're going to send a messenger, it's going to take you 10 hours to perhaps fix it. So that's why many of the flights, like for instance, the Mars lander and so on and so forth, are programmed to do what they need to do, and then they figure it out when they get the signal back that they're on Mars and such. So you just can't instantaneously fix something out there. But again, this is by radio wave. It takes 5 hours to send the message and 5 hours for it to come back. How about Proxima Centauri? Well, let's have John stay here and say hello to Mary, who's at Proxima Centauri, and he says hello to her. Okay. And by the way, John is 48 years old and Mary is 46, by the way. So what's going to happen is Mary's going to hear from him when she's 50 years old, because it's going to take 4.25 years for that message to get there. And when she says hello back, it's another 4.5 years. So John's going to be nearly 58 when he hears back, 57, somewhere around that time. All right. So there you have Proxima Centauri, but let's talk about going across from one side of the galaxy to the other. And John says hello to Mary, and Mary will hear about him from him in 100,000 years. Humans have been on this planet about 100,000 years, so it would take all of the history of humankind for that message to get across at the speed of light. Pretty far. Of course, then she's got to answer him, and that's another 100,000 years. So you got 200,000 years in the communication. How about calling somebody that's living in a planet that's going around a star in the galaxy of Andromeda? And John says hello, and it's going to take 2 million years for that message to get across. So stars are other than our sun, are so far distant that astronomers speak in their distance not in terms of kilometers or miles, but in light years. Light year is the fastest moving stuff in the universe. If we simply express light years as miles or kilometers, we end up with impossibly huge numbers. But the 20th century astronomer Robert Burnham Jr., author of the Burnham's Celestial Handbook, devised an ingenious way to portray the distance of 1 light year and ultimately expressing the distance scale of the universe in understandable terms. He did this by relating the light year to the astronomical unit of the Earth sun distance. And you can see this on the chart here. Okay, moving on. Now let's talk about size. That kind of gives you the idea about distance, but let's talk about size. Well, when I go to a group, I usually say, who's the shortest person in the room and who's the tallest person? That's why this is up there. And then that person stands up and I will say to them, well, how about if Shaquille O'Neal walks into the room, how tall do you feel now? You know, and the person always says, well, I feel kind of short now, right? Well, let's take a look at one thing. Let's take an elephant compared to a human. Now, if an elephant was on the basketball court, he could push Shaquille out of the way pretty easily, couldn't he? So how big is tall really when you compare it to an elephant? But an elephant is pretty large, right? Unless you start comparing it to other things, like, for instance, a T-Rex in this picture and a patasaur. The patasaur was somewhere around 60 feet long and weighed several 100 tons or close to that, 50 tons. I don't know the exact number, but substantially heavier than and larger than a human on this picture. Even then, you can go up into another size. How about an elephant? There's the human there at the corner. There's an Indricotherium, which was the largest mammal that ever lived on the earth. And there's the Tyrannosaurus Rex. And there's a Brachiosaur, which was a huge dinosaur. And then you have a Quetzalcoatlus, which is that flying one there. And of course, the blue whale, which is the largest living species on this planet of animal life, obviously. But if we take that big blue whale, the sulfur bottom whale, and we put him in the front of the city of New York, Well, not so big anymore, is it? When you take a look at all those buildings. How about New York? Let's take a look at New York on the size compared to the United States. Can you see any of the buildings in this picture? Obviously not, because the New York is much smaller than the United States of America. How about that, taking the United States and comparing it to the Earth? How about New York? Can you see New York right there easily? No, of course not, because the Earth is much larger. Now, just as a little idea, there's the moon in comparison to the Earth, and there's the largest of the asteroid series. It is a minor planet, of course, and that kind of gives you an idea of the largest asteroid compared to the Earth, and of course the moon to the Earth, and that's obviously a substantial difference when you take a look at them. But here you have this P67 Churyumov-Gerasimenko, which was a comet that we looked at. We actually sent a probe to look at it and actually land on it. Didn't work out very well, but there's the city of Los Angeles compared to this comet. Now let's take a look at the terrestrial planets. Here's the Earth. The Earth is the largest of our terrestrial planets, and Venus is second largest, and there's Mars, and there's Mercury, and just to throw in that Pluto, just to give you another idea as to size, and you can see that the Earth is large and Pluto is small. But if we take the Earth and we shrink it down there, you can see it in the front of the picture. And there's Venus and Mars and Mercury and Pluto. And then you have the ice giants, Uranus and Neptune. And by the way, it is Uranus, not Uranus, Uranus and Neptune. And by the way, I'm going to tell you something just as a side note on that. Actually, this and the Earth are the only two planets that are not named after Roman gods. Uranus is actually spelled Oeraunus, and it is actually the god of the skies. And that's Uranus, just a little piece of trivia for you. And there's Neptune. And then you have the two largest planets in our solar system. You have Saturn, which is about 71,500 miles in diameter. And then you have Jupiter, which is 86,800 miles in diameter. I'm almost embarrassed, I know that. But anyway, there you have the planets, and look at the size of the Earth in comparison to Jupiter. So Jupiter would be considered very large, and the Earth not so much. There's North America compared to the red spot on Jupiter, just to give you an idea of a storm that's pretty intense and pretty big. And there's just North America next to it. As a matter of fact, if you compare the Earth to Saturn, you could take 6 Earths and stretch it out from the planet's surface right to the end of the rings. And that kind of gives you an idea of the size of Saturn. Well, those planets are mighty big, we know, but let's take them and compare them to the sun. Well, compared to the sun, even giant Jupiter is dwarfed, as you can see, and there's a little speck called the Earth right there. To give you an idea how large the sun is, that's the orbit of the moon going around the sun, going around the Earth, and you could take the entire orbit of the moon and put it inside the diameter of the sun. As a matter of fact, here's a representative of the Earth and the moon in their relative size and distance. You can see the moon out there and you see the Earth, and you could actually fit all the planets between them. All the diameters of the planet totaled up would stretch and be within the size, the distance of the Earth to the moon system. And remembering how big the sun is and the entire system, which would be double that top picture there, and you could take all the planets twice and put them across, and they would still be smaller than the sun. Let's take a look at the Earth in comparison to the solar system. Very tiny, as you can tell. This is not a very, very clear one, but you can kind of see how the solar system matches up, and you can see that this is it's to show you how small the Earth and the sun and the rest of the planets are just to our solar system itself. Now let's go take a look at some of the stars. Here's the sun. Sun is a relatively moderate sized star, considering how it goes in space. But the brightest star in the sky is Sirius. And Sirius is a winter star in the constellation of Canis Major. And then there is a star that's relatively close to us called Wolf 359. If you ever watch Star Trek, sometimes they talk about passing Wolf 359. Wolf 359 is approximately 6 light years away. And there's Jupiter to show you. Wolf 359 is a red dwarf star, and those are the most populous in the universe. There's our sun, and there is Sirius. Now we take the sun and we shrink it again. And look at this. There's Sirius next to it, and we go to Pollux. That's the beta star in the constellation of Gemini. And that star is considered a red giant star, and is just pretty much large enough to possibly, in fact, become a nova. We don't know that. Supernova, it may be, but we're not sure of that. And of course, Arcturus is the brightest star in the summer sky. And you can see that it's, if you take the tail of the Big Dipper and you wrap it around, you will run right into Arcturus. Arcturus is a red giant, but a giant star. And that one almost for suredly will at some time collapse and probably explode at some point. Now, those are pretty big stars compared to the sun. Look how the sun and Jupiter there is you can't see Jupiter against that because it would be about a pixel, you know, and the Earth is, of course, invisible in this type of shot. Now we take Arcturus and we shrink it down. Do you see the third star on the very bottom? There's the sun, which is a pixel. Then you have Sirius. Then you have Pollux, and then you have Arcturus. And that's considered a giant star, Arcturus. But if you take a look at Rigel, which is the beta star in Orion, it is a white giant star. It absolutely will explode sometime. And then you go to Aldebaran, which is the eye of the bull in Taurus. And that's a red, considered now at the border of what is known as a hypergiant star. Then you have Betelgeuse. Betelgeuse is the alpha star in Orion, and that is going to explode next in the area. So at some point in the time, we may in fact get a chance to see it actually blow up. It will blow up sometime in the next 100,000 years. So chances are pretty small, but it could. It's at that point. Then you have Antares. By the way, Antares is named, that's a hypergiant. Antares is the eye of the scorpion. And of course you have Antares, oh, maybe it's the tail of the scorpion, I don't remember which, but it doesn't matter, it's in the scorpion. And Antares is a hypergiant, much larger than Betelgeuse, and it will explode at some point in the future. It is called Antares because Mars' Greek name is Ares, and since this is a red star and Mars is red, when they're near each other, it's on the ecliptic, so they get near each other. They are, this is the anti-Mars, if you want to call it. That's how it got its name, Antares. Let's move along. Got Antares now, and we've shrunk it down again, haven't we? And now we have Enceladus, is a star that actually inhabits the Small Magellanic Cloud. It is a blue hypergiant, and it's likely to go pretty quickly because they don't live that long. They burn up their fuel very, very fast. And then you have KY Cygni, which is even another hypergiant, and then VV Cephei is a huge. And we have another picture of Betelgeuse again against Mu Cephei, VV Cephei, and VY Canis Majoris. VY Canis Majoris is one of the very largest stars, and actually it could be the largest star we've ever discovered. Just to give you an idea of how big VY Canis Majoris is, there is our solar system. The orbit of Saturn actually would be within the diameter of VY Canis Majoris. And to give you an idea also, as far as our sun is concerned, there's a picture of our sun, and we've blown up the picture 7 times in order to even be able to visualize our little sun. There is probably another star that's a little larger than VY Canis Majoris. It's called UY Scuti, and UY Scuti is also, we've done the same thing with that. Okay, that kind of gives you an idea of some of the stars and how big they are, and you can remember back to you compared to an elephant, and then go on up there, and you can see that there are objects in there that are really, really great. It is only 30 times the mass of the sun, that is UY Scuti, but it has a radius of more than 1,700 times greater than the sun. How about the biggest black hole? The big black hole that we've kind of picked out is NGC 1277, and it has an orbit that is 4 light days wide, meaning, again, it takes 8 minutes to get to the sun, of course, in the speed of light, and 5 hours to get to Neptune, as you can get an idea. But again, it would take 4 days for light to travel across this black hole. And you can see the orbit of Neptune within it. And of course, there's a little arrow to the orbit of the Earth, which is infinitesimal in comparison. Kind of give a comparison, you take a white corpuscle and compare it to the sun as equal. The United States would be equal to Andromeda in that same scale, to give you an idea of real scale. This is our interstellar neighborhood. It shows where many of the stars are in there. You can see Sirius, you can see Proxima. I think I might be able to even get over there. See that? No, it won't do that. Okay. Anyway, you can see all these different stars that are in our very, very local neighborhood, understanding that this is a distance of several 20 some odd light years and such. And every star that you would see at night, every star is within that little circle that you see on here compared to the Milky Way. So every star is there, in there, that you see at night. Everything else is in the distance. And our local galactic group, there's the Milky Way, and you have the Andromeda Galaxy. You can see that this is about 1 million light years scale at the top. So this is about, I'd say 8 to 10 million light years across. Andromeda and the Milky Way, as we said, is 2 million light years apart. So you can just kind of see the distance of all these local galaxies. And we are all members of what is known as the Virgo supercluster. And there you can see the Virgo supercluster right in that, on the right side of the screen there. And you can see all these other groups of galaxies. And then you can take a whole thing and look at it from all the galaxies, that the local superclusters, and these are again the local superclusters. So this is a large area, obviously, of the sky that you can see all these stars and these galaxies. Of course, these are telescopic for the most part. Taking a look at the observable universe, you're there. The observable universe is estimated at 92 billion light years across. And that is the observable universe that we have in. This is the known universe. There have been speculations, of course, that in fact there are many universes. It's a multi-universe system. And as a multi-universe system, there could be billions and billions of them out there. We don't know that for sure. And we don't know whether this is it. So you can give an idea of how little and insignificant we are as a species and such, and as a planet. Are there other life forms in the universe? That's hard to say. Probably there are, because everywhere we look in our known universe, the stuff that makes up the baryonic matter is all the same stuff. It's all oxygen and carbon and hydrogen and helium, and all those elements are out there. And carbon is one of the only elements that is capable of linking up with other elements. That doesn't even talk about dark energy or dark matter. That's a whole different subject, and scientists don't even know exactly what that is. And now you're open for any questions that you might have for me.
All right. Yeah, we've had a few folks up and watching, and but before, and a couple of people said hello. Sherry says hello, and but I had a question. Do you think there's life elsewhere? And within your answer, can you relate that to what you've been talking about here, the size and distance of the universe?
Well, let me take a couple of shots at this. All right, that's a very interesting subject for me through history as well. I believe that life is endemic in the universe. I think it's everywhere. I think that the stuff is there to make them. Once you have an exploding star, you get all the elements that you need to put together a life form. But let's talk about what life is. First of all, as far as intelligent life is concerned, I have some questions as to whether there's any here on Earth, but that's another thing entirely. But what I'm saying is, as far as a life form is concerned, understand the differences that would occur. To give you an idea, your DNA, 50% of your DNA is the same DNA that a banana has. All right. So what we have is we have a source of origination. This planet has gone through some dramatic changes through time, and life forms have changed because we had the draconian event, which destroyed all the life on the Earth pretty much, except for very microscopic life there was no oxygen here. Oxygen was produced, and then the oxygen-bearing things came later on, a 100 million years later, and that's when we started developing the other life forms. Now, this type of thing would have to happen someplace else, and whether the life forms would evolve on a situation that never had any oxygen, for example, that's a possibility. We don't know that for sure. So when we talk about life in the universe, would we recognize it as a life form or not? And if we did, it wouldn't look like us. You don't, all those things you see on Star Wars and Star Trek, it's ridiculous. You could have a walking tree somewhere else, or something that's completely disassociated. It could be an octopus, that type thing, if it was close to us in generation. Would they be able to relate to us as far as our emotions are concerned? And let's just talk about the Earth, for example. Let's take a planet that's just a little bigger, that has a greater gravity, or it has a different atmosphere. Maybe it's 27% oxygen and the rest nitrogen, or maybe it's 50% oxygen. What kind of life form would you get from that? Would they be able to think to, in fact, take off from the planet? We have other animals on this planet that are probably nearly as smart as we are. Dolphins, for example. Have you ever seen a dolphin rocket ship? I'm saying. Are they interested in doing any of the things? Are the things such as love? Is there politics? Is there compassion? Are they look like us? Do they have schools? Do they have all those other things that we go and talk about all the time? They could be completely different than us. Now, as far as life forms are concerned, again, I believe it's endemic in the universe. But anything like us, we're never going to see anything that looks like us. The other problem is I had this question at last year's astronomy at the beach. Somebody came up to me and says, I believe there have been aliens here. And I want to argue the point. And I asked him this question. I says, do you answer one question for me? Do you believe the laws of physics can be broken? He says, yes. And I said that we have nothing to discuss. Because if the laws of physics can be broken, everything's out the window. I don't believe they can be. They could be, but I don't think they can be. But if the laws of physics can't be broken, you saw the distances and how long it takes to get there, and you cannot exceed the speed of light. If you can't exceed the speed of light, you ain't going anywhere. Now, you could have eternal life, and you could send ships there and do all those type of things. Perhaps we don't know that. But again, based on what we know now, the likelihood is we've never been visited. And who would be interested? We don't have the resources. You can get all the resources you can get on the Earth on Titan. What do you have to go to a planet that has beings on it? So there you go.
Excellent. Well, we've got an observation and another question.
Go ahead.
The observation is from Jim that had been it's been making the rounds a few years ago as far as size of the universe. If the Earth was 1 pixel, depending on the size of your computer screen, it takes 1,500 displays to reach Pluto.
There you go.
So that was just another way of explaining the immensity.
Amazing.
Of just getting out there to Pluto.
Thank you, Jim. Thank you very
Jim.
much. That was good, Jim. I'm stealing it.
And then we have 2 more that have come in. Jacob asks, how does the larger size and comparatively small mass of Scuti affect its properties compared to our sun? Properties such as stability, lifespan, etc.
Okay. When you talk about stars, you have to understand the life of a star. A star forms out of gas, all right? And it gets to a certain diameter, all right? Now, the diameter also has to do with how much stuff there is. Now, some things collapse down and complete collapse down and become very, very dense, like blue white stars and such. A star like Scuti is loose material. You could actually probably pass through it if it wasn't so hot pretty easily, because it really doesn't have a great mass. We don't know how much mass is in the center of it too. That's another thing because of the great pressures. So how does it affect it? Well, can planets go around it? Sure, I'm certain. But again, when you got red stars, big giant red stars, they're not going to have a whole lot of the heavier elements, generally speaking. That's generally the case. But again, we don't know for sure. It doesn't all blow that rule. Did I answer his question?
I believe so.
Okay.
And the last question has come in from James is the universe still expanding from the Big Bang as we speak?
I love this question. That's a great question, James. I'm enjoying it. At this point in time, we've discovered that the universe is in fact expanding at a greater rate all the time. It's increasing rate. As a matter of fact, an interesting thing of traveling the speed of light, actually the universe is expanding at faster than the speed of light. And you go, how can you say that? Well, it's the expansion of the universe, not the expansion of the objects. So the point is that the objects can't move faster than the speed of light, but the expansion of the universe can. So that means that it expands at greater than the speed of light. Take a look at the size of the universe. It's 92 billion light years across. If you started forming 13 billion light years ago, how could it be 92 billion? And the reason is because it's going in all directions and it's going faster and faster all the time. So there's your answer to it. Again, that's our known universe. Is it running into other universes? We don't know for sure.
Well, we've got another one. Is faster than light? Mike asks, is faster than light travel possible without breaking the laws of physics and theory? We just haven't developed the technology or engineering or harnessed the power required?
Physics says you can't go faster than the speed of light. Here's the reason why. The reason is because as you approach the speed of light, time slows down. And you cannot, and when you get to the speed of light, you are infinitely large and infinite, and you can't be infinite. That's a law of physics. You can't be infinite. So you can get close to the speed of light. Yeah, technically you can. You can get close to the speed of light. By the way, that's an interesting story because it promotes one more thing. If you travel to the center of the Milky Way, for example, going at the speed of light, let's say 99.999%, because we can't go to it, right? It would take you 42 years to get to the center of the universe ship time, 42 years. And then you would turn around and you would go at nearly the speed of light back home, and you in your ship would have aged 84 years. The people on Earth, they would have aged 52,000 years, and most of your friends would be gone by that time.
Wow. Well, I think we've come to the end, and Ken, you have made an immense topic manageable, and it is the immense of this universe is so hard to comprehend, but you've helped me at least get our arms around what's going on out there. Oh, Sherry's got one last question before we sign off.
Sure.
You got time for one more?
Yep, sure. I got all the time you need.
Okay, Sherry asks, so we are measuring size or distance by each celestial body. How would you suggest changing the explanation to include other things, to show size, depth, or distance of dark matter or void?
Well, again, that's a question that scientists are grappling with right now. We know that that baryonic matter, that's the light you see, probably takes up only 5% of the universe. That means that everything else is either dark energy or dark matter. Dark matter, we know, is there because when we measure the density of the galaxies that we look at, we can see that the measurements by the scientific stuff that they use do not measure up to the amount of baryonic matters there. So something else is there, is what we're saying. Also, what's pushing the universe to expand? And that is what is known as dark energy. You know that there's only two things. There's only energy and matter. You just take a piece of wood and you burn it. the fire is energy. All right. So either things are matter or energy. Even at the Big Bang, it was all energy. And then all of a sudden it transposed into this matter from energy, which it can happen. And again, there's the positive and negative stuff and everything, but you don't even know that. But again, that's what we're talking about. So do we know? Not for sure. We really cannot tell you what dark energy is. We will figure it out. There's a thing called, what's the name of the object? WIMPs. They're called, a WIMP is a large piece of something like that. That's what they're talking about. The matter is this thing called a WIMP. And we don't know if that's real or not, but that's the name they put on it. But again, you're talking about 5% baryonic matter, 25% dark matter, and somewhere around 70%, 65 to 70% dark energy, which is what makes up our known universe. Okay? Did that help you?
That's great. Well, that brings us to the end. You've brought an immense topic down to earth. Thank you, Ken. Very enjoyable. And Sherry has just typed her thanks into the chat. And so thank you so much, Ken. This has been a great talk. And
I have one last thing to say.
Yes, sir.
When you think about the universe, you truly have to think out of the box. That's what you have to think of. Get out of the box. Do not contain yourself.
Absolutely. All right. So thank you so much. And we're going to end the meeting, and people can listen to some of the other ones. Oh, folks, if you can, there's a satisfaction survey on the website, so you can tell us what you think. And please pay attention to all the other presentations that will be happening tonight and tomorrow.